very good morning and welcome to this course on the foundations of continuum mechanics. Today we'll be talking about the Lagrangian form of the momentum equation. So let us get started. So let us recall the Cauchy stress tensor first. So for a given point P, the stress tensor sigma was a collection of the three traction vectors on three mutually perpendicular cutting planes along the coordinate directions. So for a Cartesian coordinate system, O, x1, x2, x3, for a point P, we defined three cutting planes, one along the E1 direction, one along the E2 direction, and the third one along the E3 hat direction. So these are the green, the blue, and the red cutting planes. And this stress tensor basically was the collection of the three traction vectors on these three mutually perpendicular cutting planes along the coordinate directions. And this sigma was called the Cauchy stress tensor. And the reason we defined a Cauchy stress tensor was that through the Cauchy stress formula, we could write the traction vector on any arbitrary cutting plane passing through point P as sigma ji and j. In fact, if we go back further, we define the traction vector using the Cauchy stress principle as this, where the small force delta F was the force acting on an area delta gamma, which can be shown as this. So this is a small area delta gamma, and the outward normal for this area is n hat, and the small force is delta F, which is acting on this small area, the normal n hat, and this surface force delta F is a force acting because of the other part of the body or some boundary condition on the point P on this cutting plane. Now we also noted that if I change the cutting plane, that is I choose to slice the body still passing through the point P, but along a different cutting plane, my delta F will change. So delta F is written with a superscript n hat. So as per this Cauchy stress principle, the ratio of this delta F to the small area delta gamma under the limit delta gamma approaching to 0, and this ratio converges to the traction Tn hat. So this was basically the definition of traction, also known as the stress vector. So in the end, it's all about being able to calculate the force delta F. So this delta F or dF on the cutting plane with the normal n hat is ultimately given as the traction times d gamma, which in terms of the Cauchy stress tensor is written as n dot sigma times d gamma. So this was a quick recall into the Cauchy stress formula, which was used to define the Cauchy stress tensor sigma, and the Cauchy stress principle, which allows us to use this sigma to calculate ultimately the infinitesimal surface force dF. Now if you want the total surface force, all you have to do is you have to integrate this infinitesimal surface force over the total area gamma. Now when we had the discussion on stress, we had not talked about the different configurations. But now that we talk about a reference configuration and a current configuration, we will say that our n hat that we've been talking about in the Cauchy stress tensor is an n hat which is defined for the current configuration. So it is expressed in the spatial coordinate system. So if you're expressing n hat in the spatial coordinate system, that means we write this as ni ei hat, because ei hats are the basis vectors in the spatial coordinate system. And this is because our analysis is typically performed for the current configuration. Similarly, we define the traction vector t n hat also in the spatial coordinate system. So it's written as ti n hat ei, because we are performing this analysis in the current configuration. So we also express the traction vector in the current configuration. So this is our body, and this is our infinitesimal area d gamma with a normal n hat and a small force acting on it, which is df superscript n hat. Then we can define the total surface force on the bounding surface as the integral of this infinitesimal force df, which is acting in the n hat plane, and this we integrate over the total surface area, and this is a closed integral because it's an integral over the bounding surface. And using the idea of traction, we can write this as Tn hat times d gamma, and as you move your point P along the surface of the body, the d gamma changes as well as the traction corresponding to that d gamma also changes, which using the Cauchy stress principle can be written as n dot sigma times d gamma. So this is the use case of defining a Cauchy stress tensor, that you can use it to find the infinitesimal force acting on a surface d gamma, and then you integrate that to get the total force acting on the surface of the body. Now, when you talk about the current configuration, so let us say we're talking about a point Q in the current configuration, and there is an area d gamma around the point Q, which basically includes the neighboring points or the neighborhood of Q. The outward normal is n hat, and the small force acting is d f n hat for this current configuration. Now, if I trace it back to the reference configuration, and let us say this point Q in the reference configuration was somewhere here. So the surface area was like this, and the outward normal was like this with a capital N hat direction, because the direction could be different and the area could be different. So we call this d gamma with a naught on top to denote that we're talking about the reference configuration. So as I said, the point Q, small q, has an infinitesimal area d gamma around it with an outward normal small n hat in the current configuration. And this current configuration, it came from a reference configuration through some deformation, which was defined as x as a function of capital X and t. And we say that this q corresponds to a capital Q in the reference configuration with the same neighboring points forming an area d gamma naught, because the deformation could have resulted in the change of area, and the direction of the outward normal to the area was capital N hat. So this capital N hat corresponds to small n hat, that is the points on the surface which were forming an area pointing in capital N hat direction, now after deformation form an area and point an outward normal in the small n hat direction. So in the reference configuration, they had an outward normal capital N hat, which was expressed in the material coordinate system. That is because we prefer to express quantities in the reference configuration using the material coordinate system. So we'll write our n hat as NA IA hat. So now, similar to the Cauchy stress principle, we can state that the ratio of the infinitesimal force df n hat, that is acting on an area d gamma in the current configuration, divided by d gamma naught. So again recall that we have a reference configuration and we have a current configuration, and this point Q, which has an area d gamma around it with a normal small n hat, has a force acting df n hat on it, and the same point was capital Q with an area d gamma naught and a normal capital N hat. Instead of having a d gamma here, as we had in the Cauchy stress principle, we have a d gamma naught corresponding to the area that the collection of particles in the current configuration assumed in the reference configuration. And this ratio, because we have a different denominator here, will approach a vector which this time will denote by small p vector instead of small t vector, and we put a capital N hat as a superscript because now we're tracking the areas in the reference configuration. So it's like saying that this force dF is acting on an area which assumed an area d gamma naught with a normal n hat in the reference configuration. Because in the Lagrangian expression, we tend to track the points and the areas and their unit normals in the reference configuration. Of course, the force that we're talking about is still in the current configuration because the force balance is still being done on the forces acting on particles in the current configuration. So this will allow us to write our infinitesimal force dF n hat as the new stress vector P capital N hat times d gamma naught. And since our infinitesimal force is still written for the current configuration, because we're interested in the force balance in the current configuration, so this will be expressed in the spatial coordinate system. So the bases are still the vectors E hats, not I hats. And since the stress vector P is along dF, so we also express that in the spatial coordinate system. So P vector is written as Pi Ei hat. So this new stress vector, that's P superscript capital N hat, is defined for surfaces with the normal, that is capital N hat in this case, expressed in the material coordinates, and area, that is d gamma naught, which is written in the reference configuration. So now we're tracking points and areas in the reference configuration. So the area is written as d gamma naught and the normal to the area is written as capital N hat. So this stress vector is tracking the force that is acting on areas which were assuming a certain area and normals in the reference configuration, but its components, that is the components of the vector P, are still expressed in the spatial coordinates, because this stress vector P is ultimately going to give us this force dF, which is a force acting on the point Q in the current configuration. As the current configuration changes to a newer configuration, then this force will change. But if you're talking about a point Q, which may go to another location in the newer configuration, it still would be tracked to the same location in the reference configuration, and the points around Q will still have the same area d gamma naught in the reference configuration and the same normal capital N hat in the reference configuration. And remember, we are doing all this to be able to write the momentum equation in the Lagrangian coordinate system. So that is the reason we are trying to go back to the reference configuration for locating points and areas. So now we'll be making use of this new stress vector, that is P n hat, for writing our momentum equation. So let us do that. So we still state the momentum principle for the current configuration. So the equation is exactly the same as we had written earlier. So the time rate change of the linear momentum, which is written as rho bi dot, where the d by dt goes on the velocity like this. This is equal to sum of the body forces and the surface forces acting on the body or a sub-volume that we have assumed to consider. So now we'll express all the quantities in this equation in their Lagrangian description. On the left hand side, our rho becomes a rho tilde, Vi becomes a Vi tilde, and d omega becomes a j times d omega naught. So the integral now happens over the reference volume omega naught. On the right hand side, again a rho becomes a rho tilde, Bi becomes a Bi tilde, and d omega becomes a j times d omega tilde, plus now this integral, which is integral of the forces, we express this df vector as the new stress vector P with a superscript n hat multiplied by d gamma naught. So as we stated, our modified form of the Cauchy stress principle, that this df is written as the stress vector P times d gamma naught. But since we are expressing the stress vector P in the Lagrangian description, so we put a tilde on the top as well. So the tilde over any quantity r means that it is expressed in the Lagrangian coordinates. So P tilde means that this is expressed in the Lagrangian coordinates. Now in the above equation, I will combine the terms rho tilde and j together. I'll tell you why. So recall that from the Lagrangian form of the conservation of mass equation, rho tilde times j was given as rho naught, where rho naught is rho tilde written in the Lagrangian description at t equal to 0. That is, it is the density field in the reference configuration. So using this relation, our intermediate expression for the Lagrangian form of the linear momentum equation becomes, let us box this equation and we'll give it a label A. So we're almost there, except that we still have to do something about this term here, because earlier when talking about the Eulerian form, we had expressed this in terms of some stress tensor. But here we still have a stress vector. Let us talk about this stress vector P a bit more. So just like we had in our previous Eulerian traction vector, this P stress vector on a surface with a unit normal n hat becomes negative of stress vector written on an area with an opposite normal. So this is exactly the same as we had got for the Eulerian traction vector T. I reiterate the fact that this traction vector P is still expressed in the spatial coordinate system, because this traction vector P is used to write the infinitesimal force acting on the area in the current configuration. Because we are doing force balance or writing the momentum principle for the current configuration. And third, if you recall that for the Cauchy stress vector, we had written the traction vector on an arbitrary normal n hat in terms of the traction vectors on three mutually perpendicular coordinate planes dotted with the normal of the cutting plane for which we are interested to write the traction. And this is the cornerstone of the stress analysis that helps us define the stress tensor, in this case the Cauchy stress tensor, sigma ji. So the three rows of the Cauchy stress tensor were the three traction vectors acting on the three mutually perpendicular coordinate planes. And this we had shown by doing a force equilibrium on a tetrahedral element and then contracting the element to a point. If we do the same thing for our stress vector P, for this case, by writing the areas in the reference configuration and expressing the forces in the current configuration, we can write the stress vector on an area in the reference configuration with a unit normal capital N hat using the stress vectors on three mutually perpendicular cutting planes in the reference configuration along the coordinate directions times NA, which is the components of the normal in the reference configuration. So if you have the information of the stress vectors P on the three mutually perpendicular cutting planes along the coordinate directions I1 hat, I2 hat and I3 hat, then you can find the stress vector on a cutting plane with a normal capital N hat in the reference configuration. And with this idea, we can now define a new stress tensor, which we write with a capital P, indices A and I, which is the stress vector P on the IA plane in the small I direction. So this small I index denotes the component along the spatial coordinate system, and the capital A index denotes the component along the material coordinate for expressing the normal to the area on which the stress vector has been written. And this is known as the first Piola-Kirchhoff stress tensor. So the Cauchy stress tensor is not the only stress tensor. We have others as well. And this is another one, which is called the first Piola-Kirchhoff stress tensor. We also write this as PK1 sometimes. So using this first Piola-Kirchhoff stress tensor, we can express the stress vector on an arbitrary cutting plane with a normal in the reference configuration along capital N hat as PAI NA. Just like we had written the Eulerian traction vector along small n hat as sigma ji nj. Now you may notice that sometimes I write a p with a tilde on top and sometimes I do not write a tilde. So strictly speaking, a tilde means that this is Lagrangian description, and a lack of tilde means it's an Eulerian description. But since this pk1 stress tensor is used for writing the Lagrangian form of the equations, almost always it has a tilde on top of it. So for the discussion now, I will choose to omit the tilde, but that may still mean that it is a Lagrangian description of the quantity. So the rows of this pk1 stress tensor, they basically denote the stress vectors written on areas with a unit normal along I1 hat, I2 hat, and I3 hat. Now, if you look at the equation A here, we will be substituting our stress vector P tilde here using the first Piola-Kirchhoff stress tensor. So let's do that. So we see that the stress vector now becomes PAINA, and I've also chosen to write VI tilde dot as AI, the acceleration field. And this term on the far right can be written as a volume integral using the Gauss's theorem. So this becomes PAI comma A d omega naught. And now, since all of these are volume integrals, I can combine them all into one integral. And since the choice of omega or correspondingly omega naught was arbitrary, so that means this quantity, the integrand, has to be 0. And this is our equation of motion expressed in the Lagrangian form. Now, as a special case of this, if we have equilibrium, that is, the acceleration field is 0, we get the equilibrium equation in the Lagrangian form. So now we'll move on to a discussion on the angular momentum principle expressed in the Lagrangian form. Now, for this discussion on the angular momentum principle, we will assume equilibrium, which will make the work easy, but the discussion is still valid for situations where the time rate change of the angular momentum is non-zero. So if we assume equilibrium, that means that d by dt of L naught is a 0. So this means that the net torque about the origin, in this case, since we are applying the angular momentum principle around origin, will be 0. So this will include the torque or the moment of body forces and the moment of surface forces, all summing to be 0 around the point O. Also remember that we are still doing this for the current configuration. So we write the moment of infinitesimal forces around the origin in the current configuration. So let's first write the moment of the surface force dF. In the initial notation, that becomes epsilon ijk. Then we have a position vector xj, which is crossed with the force delta f n hat. The delta f n hat can be written using the stress vector p with a capital N hat times d gamma naught, and we integrate this over gamma naught. And then we have the moment of the body force rho bi, so that's an epsilon ijk xj times rho bi times d omega, because this rho bi is written in the current configuration. And this is equal to 0 because we are assuming the net torque to be 0. Now, since we want to express things in the material configuration, I'll write the second integral in the reference configuration as well. So I express my rho in the Lagrangian description, bi in the Lagrangian description, and d omega becomes a j times d omega naught, and now the integral happens on omega naught. This is a 0. And this rho tilde times j is rho naught. So this becomes integral over omega naught epsilon ijk xj rho naught bk tilde d omega naught. And in fact, I'll also express my stress vector P using the pk1 stress tensor. So this becomes capital P AK times NA d gamma naught. So as usual, I apply the Gauss's theorem first, which results in this integral, and the other volume integral stays the same. So let's combine them into one integral. And since my omega naught was arbitrary, the integrand is a 0. So this is what we get. Now if you look at this term, for the condition of equilibrium, this is a 0. We just showed that as the material form of the equilibrium equation. So this ultimately results in, and similar to the analysis that we had performed earlier in the angular momentum principle being applied to the Cauchy stress tensor, we have a skew symmetric tensor in J and K. So this has to be symmetric in J and K for this to be 0. So we get this condition for x j comma a p a k. So this also means that pk1 is not symmetric. It is xj comma a times pak that is symmetric. The tensor pak is not symmetric. And that's a very important point because unlike the Cauchy stress tensor, this is a non-symmetric tensor. But we do like symmetric tensors. So we form another tensor using pk1. We define a tensor capital SAB such that PAI is xi comma b times SBA, and SAB is called the second Piola-Kirchhoff stress tensor, written as PK2. And let us check if this definition of PK2 results in its symmetry. So we'll use the top relation here, which we got from the angular momentum principle. So let's call this L and this is M. So we get this equation. And then we perform some index manipulation. On the right hand side, let's say we swap indices A and B because both are repeated. So this becomes xk comma b, xj comma a, s a b, and the left hand side stays as it is. So now we can see we have an xk comma b, xk comma b, j comma a, j comma a. So we can multiply both sides by the inverses of these, and since the inverses exist, we will finally see that SBA is SAB. So that means second Piola-Kirchhoff stress tensor is indeed symmetric. And since pk2 is symmetric, it is also known as the symmetric Piola-Kirchhoff stress tensor. So now we have three stress tensors: the Cauchy stress tensor, the Piola-Kirchhoff stress tensor 1, and the Piola-Kirchhoff stress tensor 2. And the question is there a relation between these? Of course, we saw a relation between P and S, but are they related to sigma? And the answer is yes. Let us see that relationship. So all these are related through the infinitesimal force in the current configuration. So df I along n hat in the Eulerian description is written as the Cauchy traction vector times d gamma, which becomes sigma ji nj d gamma. Let's call this 1. And similarly, this force vector is written using the stress vector Pn hat times d gamma naught, which using pk1 becomes pai na d gamma naught. And we also showed a relation between d gamma and d gamma naught in the beginning of this week. So this expression we had derived. So I can also write this as the vector small nq times the magnitude of the area d gamma is equal to xa comma q times j times the magnitude d gamma naught times na, and we'll call this equation 3. So now if we use the equations 1 to 3, so from equation 1 I will express my nj times d gamma using the equation 3 expression here in terms of d gamma naught, and then from equation 2 we have pai na d gamma naught, and that's a 0. Now we have na and d gamma naught common, so we can write sigma ji xa comma j times the Jacobian minus pai times na times d gamma naught is a 0. And since the normal vector is non-zero and so is the area, so basically we get sigma ji xa comma j times the Jacobian as pai. So now you can see the relation between pk1 and the Cauchy stress tensor. I'll write these in the symbolic notation now. So on the left hand side we have xa comma j times sigma ji, and xa comma j is basically f inverse dot the sigma tensor times the Jacobian, which is a scalar, is p. So if I pre-multiply by f on both sides, I get just the j times sigma as f dot p. I'll put it in a box because this form is something we'll be using in solving problems. And if I want to bring in the Piola-Kirchhoff stress tensor 2, so we have defined pk2 as this. So if I express this in the symbolic notation here, what we have is the tensor P in the matrix form is F dot S, but this is the IA component and we have an AI component here, so we'll have to take a transpose of this for the indices to work, and this basically becomes S transpose dotted within F transpose. So in the matrix form, P is S transpose F transpose. So let's use that. And since we know that pk2 is symmetric, so we can write this as F dot S dot F transpose. So this is the relationship between the Cauchy stress tensor sigma and pk2. So let's call this W and X. Now if I consider infinitesimal deformation as a special case, then we know that for infinitesimal deformations, F is approximately identity. We have already shown that. And then the determinant of F is then approximately equal to 1. So then W would imply that J times sigma becomes approximately P, and since J is the determinant of F, this goes away. Let's write J is equal to, and if we consider X, that would imply again J is 1, sigma is approximately F dot S dot F transpose, but F is identity, so we get S. And we can conclude from these that under infinitesimal deformations, all the stress tensors degenerate to the same quantity. But for finite deformations, they may be different. So this brings us to the end of this lecture, where we developed the Lagrangian or the material form of the momentum equations, both linear and angular momentum. So the linear momentum principle, we got the Lagrangian form of the equation of motion, and when applying the angular momentum principle in the Lagrangian form, we showed that pk1 is not symmetric, but we defined a pk2 to be symmetric as a result of the angular momentum principle applied in the Lagrangian form. So we have talked about the balance of mass or the conservation of mass and the linear and the angular momentum equations. In the next session, we will talk about the energy balance, and then we'll solve a couple of problems in the same session as a tutorial. So thank you very much, and I will see you in the next lecture.